Hello, and welcome to another lecture. So we're going to look at exact equations, or actually part 2 of section 1.8. So uh, uh, part 2 of the exact equations. We already looked at them last time. So this is section 1.8 in the book. You can get the book at this URL. You can also see it in the description. You can browse it for free on the web, or get a PDF, or you can even buy a paperback if you want. All right. So a brief review of what we did last time, what exact equations are and all that. So an equation like this, you know, m times dx plus n times dy, or we could, you could divide by dx, and it might look more like, the first order equation that we've seen so far. So such an equation is exact if there is a function capital F where the x derivative of f is m and the y derivative of f is n. So basically, so that this guy is the total derivative of f, right? So if such an f exists, then what we saw last time was that if we take the y derivative of m, which would be really like taking the x and then the y derivative of f, that should be the same as taking the y and then the x derivative of f, which is the x derivative of n, right? And conversely, if we have this equation, then you can find such an f at least locally. So maybe not at all points, but sort of if you're looking near some point or some initial condition, you can get a function there. All right. So So to solve for f, to find this f. So first, if it's exact, right? If this is gonna work. So first you integrate m, because, well, you have that the f sub x is m, so you integrate m in terms of x, right? That doesn't quite necessarily solve everything. There's this extra um, this constant of integration, which actually might depend on y. So then you need to differentiate in y. You still have some unknown in the f. Differentiate in y and set it equal to n, right? And then figure out what that unknown is, and figure out then from that what f is, right? You could also do the opposite. You could start with n, integrate in y, differentiate in x, set to m. Both are fine, and you could actually do this even if the thing is not exact. It's just not going to work out, right? So, but it's best to maybe check. It's basically you can check this condition. If this condition is not satisfied, then there is no point in trying to do this integration and differentiation and integration, right? It's that's too much work. I can just check if it isn't going to work a priori. All right, let's do an example. So suppose that we're trying to solve this differential equation. Now here again, I can multiply by dx, so it's this thing times dx, this thing times dy, right? So m is x squared plus y squared, and n is this 2y times x plus 1, right? I'll let you check that this equation is exact. You can take the derivative, basically. Let me go back, show you right. Check this, right? M sub y is equal to n sub x, right? So I'll let you to check that that's true. So now let's integrate in m, differentiate in y, set it equal to n. Right. So this is the antiderivative in x of m, right? So we're treating it as a function of x, and y is a constant, right? So x squared, we anti-differentiate, we get 1/3 times x cubed. Then we have y squared is just a constant as far as x is concerned, so x y squared. And then there's the constant of integration, and that's possibly depends on y, right? Now we differentiate that in y, right? So we differentiate this thing. This guy goes away. Over here, the xy squared that's going to give you 2xy, and this a, well, whatever it is, differentiating in y, so it's a prime of y, right? And that thing is supposed to be equal to n, so that's the n here, right? So therefore, a prime is, well, if you just do a little bit of algebra, I'm going to get 2yx, right? Just 2xy. That cancels this 2xy, and I'm going to be left with 2y on the left-hand side. So that's what a prime has to be, right? So a prime is 2y. So therefore, a is, well, we could add a constant of integration, but at this point it doesn't matter. A being y squared works. All right, so now that's the only thing that I was missing from f, so f has to be this thing. Now, to solve the equation, right? I mean, if we write the equation like this, we're basically thinking of y as the dependent, x as the independent variable. So we're trying to solve for y in terms of x, and this is basically the level sets, the places where f is constant. Those are giving us the solutions, right? So we're trying to solve this equation, right? Where c is this unknown constant, it's arbitrary constant, right? I mean, we don't have any initial conditions, so we're trying to do the general solution. I mean, essentially, we do have the solution, the implicit solution. It's just this guy equals c, right? That's our implicit solution. But in this case, we can actually solve. If you everything is just as either y squared or nothing, right? So I can just move all the things that don't include y squared on one side, then factor out the y squared and divide, and you're gonna get this. Basically, you solve for y squared. You can do that, and so then you can take the the square root, right? And you get 2 plus and minus, of course. So those are your explicit solutions. At x equals -1, this is invalid because, well, it's clearly not going to work. So this equation, if I'm looking for explicitly y as a function of x, this has no solution there, right? And one place that you see why that's true is that the term before this guy, this gives 0 there, right? So if I'd write it in the sort of the standard form that, in the start of this chapter where we wrote it as the derivative in y is equal to some function of x and y, then you'd have to divide by this. And so you can't if x is -1, right? So that's why we're getting into trouble there, right? So like we should expect to get into trouble when x is -1. Now, if I think of the equation like this, well, then it does have a solution, x equals 1, right? Why? Well, oh, sorry, x equals -1, right? Well, because, what is dx? Dx is 0 on this, right? Because dx is, and there's this is a constant, right? So dx is 0. This is 0, and then over here, x plus 1 is 0. So that is 0. So both terms here are 0, and so the equation is satisfied, right? So if I'd want to solve for x in terms of y, I could do that even at x equals -1, right? Basically, that's the upshot, right? But it would be messy to solve this, right? Try solving this equals a constant for x. It's a cubic equation. Yeah. It would be messy. So let's not do it. we avoid hard work, right? That's always a good good strategy. All right. So now, so the thing that we really want to talk about today is integrating factors, and we saw integrating factors before. For linear equations, which is actually a special case of what we're doing now. So sometimes an equation of this form is not exact, but maybe you can multiply by some function u, such that this equation is exact. That's possible. For example, the linear equation is an example of this. So let's take the linear equation in the standard, standard form, the way that we looked at it, right? It was the derivative of y with respect to x plus b times y is equal to f, right? And we write it as, in this form, right? So you multiply by dx and put everything on one side. So we have this m is this guy, n is 1, right? Now, if you let r, the integrating factor, this is the integrating factor, right? And you multiply everything by this r, right? You get this equation, right? And that equation is exact, right? This would have been the m, right? If it was of this form, right? And so if we differentiate it with respect to y, we just get r times p, right? Right, because if you differentiate it with respect to y, right? Notice here, it's something that depends on x times something that depends on x times y, right? So we're differentiating in y. So it's just y times a constant as far as that differentiation is concerned, right? So it's just that constant, right? Rp. And the other thing doesn't depend on y at all. Its derivative is 0. So we get Rp over here. On the other hand, the n over here would have been r if we differentiate that with respect to x. Well, that's r prime. What is r prime? R is this guy. So if you differentiate, you get precisely that. That's how the integrating factor worked, right? Is that the derivative of r was r times p, right? That's precisely how we set this thing up, so that it would have this precise, behavior, right? Okay, so this is an exact equation. So that's basically the thing that we're interested in, right? But how do we do this in general? How do we find this u so that this equation is exact, and so that we can then apply the technique of solving, right? We can integrate the u times m in x and then differentiate it in y and set it equal to u times n, basically. So how do we find that u, right? And so what does it have to do? It's supposed to be exact, right? So if we differentiate u times m in y, we're supposed to get the same thing as differentiating u times n in x, right? Well, what is this derivative? This is just product rule. I have a product of two functions, u and m, which is functions of x and y, right? So if I differentiate in y, I get the y derivative of u times m plus u times the y derivative of m, right? And I'm supposed to get that that's the same thing as this, which for the same reason is ux times n plus u times n sub x, right? So this thing has to be equal to this thing, right? And I can, move things about, right? Basically, I do this, and I mean, that's one way to write it. Another way to write it is this thing, right? I can move this term and this term to one side, and this term and this term to the other side, and then I can factor out u, and I get this equation over here. All right, well, there's a slight problem with this. A slight, big problem with this. This is another differential equation. I mean, really, it's even a more complicated differential equation than we started with, right? We were trying to solve this, and that was an ordinary differential equation. And we came up with a partial differential equation, right? This is differential equation that includes the partial derivatives. So it's a partial differential equation. And so how does that help? Doesn't seem to help at all, right? Well, one strategy. So it's in general, it's going to be hard to find the u in general. But again, this is not going to be something that works all the time. This is going to be something that works some of the time, right? So one strategy where we can find u is to look for when u is a function of x alone. So basically when it's u of x. So then u sub x is just u prime because it's just a function of x, and u sub y is 0, right? So the equation, this equation becomes, well, the u sub y goes away, and it's just u prime times n. It's this guy. And yeah, I can move things about, right? I get a linear equation, right? Like a fairly simple linear equation. It's this function. It's some function of, you know, um, of well, unfortunately, maybe x and y, but uh, uh, if it would be a function of x only, it would be a linear equation. Let me put it that way, right? So some function times u equals u prime. So if this function happens to be a function of x alone, I have a linear equation in just x that I can now solve, right? There's no y in here anymore, right? Okay, so basically that's the thing, right? If this expression is a function of x alone, I solve this linear equation, right? And we can even write down exactly what the solution is using the integrating factor, right? It's this this guy over here, right? And similarly, if u is just a function of y, well, if we're thinking about it, what we get is, well, this would be 0, and this would be just u prime. This is a function of y now, right? And that's going to be a linear equation, linear ODE, nice ODE, as long as this thing is not, it doesn't depend on x, right? So as long as this thing, which is almost like this, but with an m here, is a function of y alone, then again we get we solve this equation. There's that minus, so that's why there's a minus here. So that's just solving this this linear equation, right? Which we know how to do. Let's do an example. So let's suppose I have this guy over here. Now, so m is this, n is this. M m sub y minus n sub x. Well, you just do it. You differentiate this in y. It's fairly simple. 2y divided by x plus 1, right? And n sub x, 0. There's no x in there, right? So that's what this is. In particular, it's not 0, so this is not exact, right? This thing is not equal to this thing, right? Not exact. However, notice that if I divide by n now, I get, well, this is the m sub y minus n x is this guy, and divide by n, that's this guy. It's 1 over x plus 1. That is a function of x alone, right? All right, so we compute this thing. That was supposed to be the integrating factor. Well, so okay, so the integral of p, right? The antiderivative of p. This is the logarithm, right? And so if log of x plus 1, we take the e. Okay, we just get x plus 1. X plus 1 works. So if I multiply by x plus 1, this thing by x plus 1, well, first one, the x plus 1 cancels. I just get x squared plus y squared. And in the second one, I get 2y times x plus 1. Aha! This was precisely our example from before. There was a reason why I did that example. That's the example we just solved, right? And this is the solution. All right, let's do another example. Let's suppose that we have this. So let's compute. This is the m. This is the n. Right? So I'm going to have 2y when I differentiate this in y. When I differentiate this in x, I just get y. So 2y minus y is y. It's not 0. It's not exact. let's look at this thing, right? Well, this thing is y over y squared, the m, is function of y alone, right? So this is the other bit. This is where we're going to be looking for an integrating factor that's a function of y alone, right? Because this thing is a function of y alone, right? Now, if we divide it by n, we wouldn't get something that's a function of x alone. So u, the integrating factor, cannot be a function of x. It has to be a function of y. But a function of y works because this thing is a function of y alone, right? So, okay, we write down the expression for we solve that linear equation for u. That's what it is. Well, you integrate 1 over y, that's log of y, you plug that in here, right? You get e to the minus ln of y, right? The minus can go inside, so it's e to the ln of 1 over y, so it's 1 over y. Right? So the equation, when I multiply by 1 over y, becomes this thing. And now this is exact. You should check that it is exact. And so we solve. So we take the y, right, which is the m, we anti-differentiate in x, so we get xy, but there's a constant of integration that depends on y, so you have xy plus a of y. Now we differentiate that. Sorry, if right here, it was one step ahead, one step behind. So this thing is when I that's the n, right? And I'm gonna rewrite the n in this way, right? That's just a little bit of algebra, right? And this is just the derivative of this guy, right? So I have to have that this thing equals this thing. So therefore, a prime has to be 1 over y. Therefore, a y is log of absolute value of y. Well, that's what that f is, right? So the implicit solution is this. And here, maybe, leave it there. We divided by y, so we should check y equals 0, right? Because maybe y equals 0 is a solution to this equation that wouldn't be a solution for this equation because it doesn't make sense, right? So does y equals 0, is it a solution? Yes, it is. If y is 0, this is 0. This is this is 0, and dy, well, it doesn't really matter that this is 0. Mainly dy dx is 0, right? Because y is a constant, right? So its derivative is 0. So yes, this equation is satisfied for the thing. So that's a solution too. So by the way, one minor, maybe somebody caught it and said, well, why didn't I ever put in the absolute values here, but I put them in here? Well, if we were looking for y being positive, I wouldn't really have to have put them in here. Now, you could put them in here. It would still work because you'd have to do it separately for positive, negative y. But it's it just makes make things complicated and doesn't really matter in the end. You're somehow, when you work this out, you get an expression here, and if that expression makes this exact, well, in some sense, that already worked for positive and negative y. That also works for positive and negative y. So I didn't really have to worry about it too much to compute the integrating factor. So usually, if you compute the integrating factor, I wouldn't worry about it too much. As long as you find an integrating factor that works, yeah, It works, right? There's no point in finding two of them, one of them being the negative. Who cares? It's uh, you know, I mean, basically, think about it, right? I mean, if y is negative, this makes absolutely no sense, right? But so you would necessarily you should then get really there should be a minus y, right? But then it's just the negative of this equation. And yeah, if one is exact, minus that equation is also exact. You can check me on that. So it didn't really matter, right? That's why I didn't worry about it. So basically, you can, as long as the integrating factor works in the end, as long as this thing is exact, it's fine, right? But here, well, I didn't know if y is positive or negative. I had better put the absolute values there, right? So that's why they're there. Okay, so that's it. So next time, so we're gonna move to the next chapter instead of going into 1.9. So we're gonna move to higher order equations. All right, so see you next time.